Okay, well, my name is Ian Alevy. I'm a postdoc at the University of Rochester, and I'm going to talk about the limit shape of the Leaky Abelian Sandpile model. I want to thank the organizers for inviting me to this conference. I've been enjoying it very much so far. Okay, so let me explain what the Leaky Abelian Sandpile model is. And for shorthand, I'll call it Leaky-ASM because it's kind of long. So it's a cellular automaton defined on a graph G with vertices V and edges E. And it takes an initial sandpile distribution, S naught, which represents the amount of sand at each vertex in the graph. And I'm going to restrict to sand being greater than or equal to 0. So I'll say that the sand pile is greater than or equal to 0 everywhere, but one difference from the usual abelian sandpile model is that I'm going to allow fractional or even real valued amounts of sand at sites. Okay, my model is leaky because it has a dissipation. This is a parameter d greater than 1. And it will evolve through a toppling unstable vertices. So let me explain what that is. The model has a threshold, and I'm going to take the threshold to be d times the degree of the vertex. So that is the number of edges incident to the vertex V. And if the initial sandpile distribution is larger than this threshold, then the site is considered unstable. And it can topple. And it topples producing a new sandpile. So what happens is the amount of sand at vertex V gets reduced by an amount d times the degree of V. And every neighbor of V will gain 1 grain of sand. Okay? Sites which are not adjacent don't change. So it's easiest to think about this in the case d equals 1, in which case there's no dissipation. And this is just the usual abelian sandpile model that some of you are probably familiar with. And in that case, the site is unstable if it has more sand than neighbors. And then it sends 1 grain of sand to each neighbor. But as soon as d is bigger than 1, then in each topple, some sand is lost. And this dissipation is going to allow us to precisely compute the limit shape of the model. Okay, so I want to talk about a particular example. And in this case, we take the graph to be Z2 with edges between nearest neighbors. And our initial sandpile consists of a delta mass at the origin. So we topple sites until stable. And you can see that after enough sites topple, you'll have a final configuration in which no more sites can topple. And that's what I've plotted here. So the colors here correspond to heights of the sandpile in the final configuration. Since we're on Z2, each site has 4 neighbors. So in the stable configuration, all sites have either 0, 1, 2, or 3 grains of sand. Okay, so the colors correspond to the grains of sand at vertices. And you see some very interesting things about this picture. For example, there are these large flat regions, okay, in the east, north, west, and south direction, where all the heights are 3. And you see an interesting fractal structure inside of the picture. And as you add more grains of sand, the picture gets bigger, but the fractal structure remains. So these flat pieces here persist, at least in simulations, as n goes to infinity. So in 2013, Pegden and Smart showed that the model has a limit shape. And their proof used techniques from PDEs to prove that it exists. However, they weren't able to compute the limit shape. By limit shape, I mean the boundary of the set of sites which have accumulated chips. Okay, so a little bit earlier in 2008, Levine and Perez gave estimates for the size of the limit shape. They showed that the limit shape is bounded between 2 circles, one of radius C1 square root of n and the other of radius C2 square root of n. But the ratio of these constants is larger than 1. So this doesn't tell us precisely what the limit shape is. It just gives us a bound. And as you see from the simulation, the limit shape has some very interesting behavior, right? This flat portion where all heights are 3, okay, if you zoom in near the boundary, there's a line here. Well, the boundary is actually flat. It's a line right here. And from simulations, it seems like this flat portion persists. So the question is, what is the shape? What is the limit shape? Is it a circle? Well, from simulations, it looks like it's not, but no one knows. Conjecturally, people think it's a polygon. Okay. And I just want to mention that this is a fairly large simulation. I'm using 10 to the 7th chips. Okay, so now I want to describe our result. And this is joint work with Sevak Makarchan. So we're looking in the case with positive dissipation. That is, each time a site fires, some chips are lost. So we let D and D be the set of sites which have accumulated sand under toppling. Notice that it depends on N, which is the number of initial chips, and D, which is the dissipation. So for D bigger than 1 and R equal to log N minus 1/2 log N, the boundary of 1 over R, D and D converges to the dual of the boundary of the gaseous phase in the amoeba of the polynomial P of ZW equals 4D minus Z minus 1 over Z minus W minus 1 over W over 4 times D minus 1. Okay, I want to make a few comments about this theorem. The first is that R here is the size of our limit shape. And if you notice, R here is roughly log N. So if we compare it to the case studied by Levine-Perez, in which there was no dissipation, they show that the limit shape is of size roughly square root of N. So it's very interesting that as soon as you introduce dissipation, the limit shape shrinks. It now becomes of size log N only. Okay, I'll mention a little bit about what amoeba are later if there's time, but I want to also comment that this polynomial here is associated to the underlying graph and to the toppling rule. And if you change the graph or change the toppling rule, you'll get a different polynomial, but you can adapt the techniques in our paper to compute the limit shape for these more general cases. So here are some simulations. On the top, I'm showing simulations of the Leaky-ASM with different values of D. So as D converges to 1, the dissipation is disappearing. And you see that the limit shape in the simulation looks circular as D gets close to 1. But as D grows, it looks less circular. And as D goes to infinity, it actually converges to a diamond. Okay, so this is with D equals 1000. On the bottom, I've shown the plots of our limit shapes given by our theorem. So our theorem gives us explicit descriptions of the limit shapes. And we can prove what happens to the limit shape as the dissipation goes to 1, and we can prove what happens as it goes to infinity. So now I want to talk a little bit about the connection between the limit shape and amoebas. For those of you who aren't familiar with amoebas, the amoeba of a polynomial is the image of its zero set under the log map. So in my case, I have a 2-variable polynomial, P of ZW, and I look at its zero set in the complex plane, and then I project that onto the map, under the map log absolute value of Z, log absolute value of W. That gives me a region in R2. That region is called the amoeba. So on the left here, what I've plotted is the boundary of the amoeba of the polynomial associated to the simple toppling rule on Z2. It's the polynomial in the theorem before. So the amoeba has components. It has these tentacles that go off to infinity. Okay, and then it has a bounded, a bubble. Sometimes it's called a gas bubble around the origin. And this is a bounded component of the complement of the amoeba. And this is going to have a very important meaning for us. So if you take the dual of this curve, okay, of the red curve here, and by dual, I mean you take the, for each point, you find its tangent line, and you think about that as a point lying in the projective dual space, you'll get a curve. And if you do that for this entire red curve, you get the red curve on the right. And we show that this curve corresponds exactly to the limit shape of the Leaky-ASM. Okay, these other curves are duals of other portions of the amoeba. All right, so now I want to connect our model to the classical ASM or the standard ASM that has been studied in the past by many people. Unfortunately, I didn't have time to discuss all of the previous work on the ASM, but there are lots of names, people like Deepak Dar and Bach and many other people. Obviously, I don't have time to get into. But Sevak and I proved the theorem that as D goes to 1, meaning that the dissipation is disappearing, the leaky ASM converges to the ASM with background height -1. That means that each site is starting with a hole of height -1. So here I have some simulations that show you what the limit shape looks like as D converges to 1. In this first picture, we see what happens when D is relatively large. Okay, there's some fractal structure appearing here, but on the inside, you don't see very much fractal structure. And this is what we saw in the case of our first theorem. You can go back to those simulations. In those simulations, you don't see this rich internal structure that the ASM has. However, as D converges to 1, so here D is closer to 1, you start to see the fractal structure appearing. And this is what the ASM looks like without any dissipation, but background height -1. You can see that the leaky ASM is really converging to the ASM. So what we hope to do is to push our techniques in this paper, which allowed us to compute the limit shape of the leaky ASM. We hope to push them to gain information about the limit shape of the ASM, which is really what people are mostly interested in. And I just want to make one comment that this is the ASM with background height -1, okay? And if you compare it to the ASM with background height 0, the pictures are similar, but there are some small differences. Although what's kind of remarkable is that you still have this fractal structure, and you still have these fractal pieces on the boundary. So all of the results I talked about today are on the archive. And thank you. I'll stop there.
Okay, so thank you. So I'll stop the recording and